Now let's take a look at this graph we constructed. What is the maximum flow size that can occur in this graph? Certainly it's upper bounded by the capacity, the total capacity out of S prime, or the total capacity into T prime. Let's take a look at those quantities. Let capital D denote the total demand in this original network, G. So we're going to sum over edges in this original network of the demand along that edge. Notice this is the same as summing over the vertices of the total demand into the vertex, because every edge has one tail, and similarly, we can count from the head of the edge, so we can sum over vertices of the total demand out of each vertex. Now in this graph, what is the total capacity out of S prime? Well, the capacity along this edge from S prime to A is defined as the demand into A. So this total capacity out of vertex S prime is the sum over vertices in the original graph of the demand into that vertex. That's equal to the quantity D. Similarly, if we look at the total capacity into the vertex T prime, that's equal to the total demand out of the vertices, which is also equal to capital D. So if we look at a valid flow F prime in this new graph G prime that we constructed, what do we know about the size of this flow F prime in this graph G prime? We know it's upper bounded by the total capacity out of S prime, or the total capacity into T prime. Both of those quantities are capital D, so the size of this flow F prime is at most capital D. Therefore, we say this flow F prime is saturating if the size of this flow F prime is capital D. This means that this flow F prime is of maximum size. So all of these edges out of S prime are fully capacitated. They're fully saturated. And all these edges into T prime are fully saturated. So in a saturating flow F prime, we've fully capacitated the edges out of S prime and fully capacitated the edges into T prime. What we're going to prove is that G, our original network, has a feasible flow if and only if this new network G prime that we constructed has a saturating flow. Once we prove this lemma, this gives us a way to find a feasible flow. What we do is we take our input to the feasible flow problem, we construct G prime, we run max flow on this graph G prime, and we check if the size of the max flow is equal to capital D, and therefore it is saturating or not. If it is a saturating flow, then we know that there is a feasible flow, and actually our proof of this lemma will give us a construction. So we can take this saturating flow F prime and construct a feasible flow F for this original network G. So what we've done so far is transform the input to the feasible flow problem into an input to the max flow problem. And now, by proving this lemma, we're going to show how to transform the solution to the saturating flow problem, or to the max flow problem on this graph G prime, into a solution to the feasible flow problem.